Bon après-midi. Oui? No? Been practicing that all day. I got it right. Brilliant. My slides good. Okay, great. Well, welcome. Thank you for coming. I'll heads up, kind of like a law of 2 feet, which is this is introduction to refactoring to functional. Introduction, I'll play emphasis on the word introduction. In essence, mean if you are a functional programmer, then leave. I'm sure there's very, very interesting talks out there. So there's going to be a lot of introductory concepts here. And as I said before, if you were in my previous session, which was the advanced version of this, which anyway, I don't like negative feedback. Positive, bring it on. I'm joking. Okay, so functional programming, I always like to start with Wikipedia because source of truth. In computer science, my kid actually said to me the other day, he said, oh, this is like this. I said, no, it's not. He said, but I read it on Wikipedia. I'm like, oh, okay. In computer science, functional programming is a programming paradigm, a style of building the structure and elements of a computer program that treats computation as evaluation of mathematical functions and avoids state and mutable data. It is declarative programming paradigm, which means programming is done with expressions. Now, what does that tell you? That I could read bloody well. There are some important things there, and I'll give you a tip. I've highlighted them in bold and in red. These are functions, avoid state, and mutable data. Also declarative and expressions. So knowing that, let's go ahead and refactor to functional. Okay? But like, you know, a lot of things, as I said, I like to ask the questions, why? Why would I want to refactor to functional? So I started to look really deep inside myself. That's just a joke. But I started to look at like some of the goals that you have when you're writing code. And my goal is, for example, to write less code. And as I've grown older, I've realized that I have less time to write code, so I really want to cut down, you know, be exact in what I write. I also like to write expressive code because I've suffered from my own incompetence of writing really crappy code that I could no longer read 3 months after I wrote it, let alone 5 years, or let alone anyone else could read it. I also want to write correct code, well, because like many things in life, you know, you go through stages. And you've all gone through the stage of writing code, and then you've all gone through the stage of finding out what a unit test is, right? Yes, good. My questions are normally yes or no. Or oui or no. Except if I ask a negative question, then you have to say si. But you knew that. So, how many of you do unit testing? Right, so that's kind of like, let's say around 60–70% of the people. How many of you believe unit testing is a good thing? That's around 89–90 amounts. That's okay, right? So, you started out with this thing called a unit test, and you're like, this is brilliant. So I can actually check that my code works without running the application. Fantastic. And then you started to decide that you need to unit test everything. And then you, when I say you, I mean me, but I find similar experiences with other people, is I realized that I need to go for 100% code coverage. And then I realized that, no, I don't need to go for 100% code coverage. And then I realized that, well, you know, it's kind of like this unit testing is okay, but it kind of like sucks. I'm going to try and do a little bit more integration testing. And then now I'm at that stage of, yes, I went up to the very, like, you know, the top of the hill of I need to test everything. And now it's kind of like I apply common sense. Have you had that curve, kind of? Yeah? Okay, good. So that's the point of like I try and write less code and I try to write correct code, and if I have to write code that doesn't need to be unit tested because it's using some library or some function or something that somebody else has tested, even better, right? Why do it yourself if you can delegate? So writing, don't take me seriously, writing performant code, and as I said, this is because Silicon Valley. How many of you are doing websites currently that scale up to 100 million users? Okay, a couple. But we still need to scale. And we need cloud computing, and we need elastic computing, and scale because Silicon Valley. So we need to do scalable code. Now, of course, there's also the concept of I just want to be part of the in crowd, so that when someone talks to me about Haskell, I don't look at them and like hey, what? Like, you know, in Spain we say like, ¿qué? Yeah, kind of like that. So yes, no, I don't want to be part of the in crowd. But I did feel like, as an outsider to functional programming, that a lot of times it felt somewhat, and I really do not mean this with any kind of negative criticism, so please take it as constructive criticism, but sometimes it does feel like an elitism in terms of, you know, functional programming is this, and that, and I'm like, maybe it's not so much, and this is why I dived into this. But it's definitely not to be part of the in crowd, but it's good to know what you're talking about, which is always fantastic. I should learn that sometimes. So, having set the goals, the next question is, can I use any language? Now, that begs the question of, to answer that, I need to know what a functional language is, right? Now, this is kind of like, what color is the sky? Kind of answer, right? Depends on who you ask, they give you a different answer, right? It depends, like any good consultant would say. A language with functions as first-class citizens, right? So that means that I can actually have this concept of functions that are first-class citizens, because we'll see throughout this talk that functions are basically the primitive building block of everything we're trying to do. It has to have higher-order functions, which basically means a function that takes a function and returns a function, or a function that takes a function or returns a function. That's what a higher order function is. Lambdas, because we like to type less. And we need lambda expressions. Top level functions with an asterisk saying it's not vital, but it's nice. Well, by top level, I mean that you can actually declare a function. So for example, in Java or in C#, you can't just have some isolated function. You have to have an object that is static, a class that's static with a static method. In JavaScript, you can just declare a function. Place it in some file and never find it again, and then try and figure out how you do namespacing in JavaScript. But that's a different issue. And immutable data. Why? Well, because we'll see that some things, you know, if we reason about less things, it makes things easier. And this concept of immutable data is quite big in functional programming, and we'll see some aspects of that. So having said that, what will I be doing this demonstration in, this talk in? I'm going to be using Kotlin. Now, if you've not heard of it, it's a programming language that we've developed at JetBrains. It's open source. We did it for the sole purpose of using it for our own tools, because for 15 years we've been using Java, and we said, let's try something. And what we looked at didn't fit that well. It's open source. It's going to be released this year. And I like it because coming from a C# background and a JavaScript background, it's very similar to C# Java. It's a language that's inspired by Groovy, by C#, by Java, by Scala, but it's concise, and it tries to limit in the number of ways that you can shoot yourself in the foot. And it is 100% interoperable with Java, so you can call Kotlin code from Java or Java code from Kotlin. But of course, you can use Java 8, you can use Java 7, up to Java 5 with the functional Java library. You can use Scala, JavaScript, Clojure, Haskell, F#, C#, OCaml, or Lisp, if you want. You know, all of those kind of are what you would call not functional, but can provide functional constructs, okay? How many of you actually here use any of those languages up there, apart from Java? Okay, any Scala, Lisp, Clojure, Haskell? All right, I could go on all day, right? JavaScript, and love it. There is a debate of whether JavaScript is a functional language, to which I always answer, if you consider it a language, then maybe, yes. I love JavaScript, by the way. I'm not putting it down. I really do. Just the less I have to write of it, the better. So, basic function syntax, just so you get the idea of what we're dealing with Kotlin. It's just a quick introduction to Kotlin so you know what you're looking at. This is a basic function, so it takes a parameter. It uses a good old Pascal / Delphi notation, which is a parameter colon the type, returns a type, and in this case, it just returns a value. Then you can have single line functions. It has type inference, so you can see that I don't need to specify the return type. It has higher order functions, so I can just pass in a lambda expression, as you can also see at the bottom. And then there's some conventions, it's similar to, I think, Groovy, if I'm not mistaken, whereby if the last parameter of a function is another function, you can drop the brackets, which give it nice DSL-ish values. Higher order functions, so here I have a function sum and a function multiply, and then I call calculate, which takes 2 integers, and a function that takes 2 integers and returns an integer, and there you can see how I can apply it to. So calculate, you can reference a function by name, similar to how you can do it in JavaScript, except here you have to put colon, colon. Same as Java, you have to put the type and then the function name, except in Kotlin you can have top-level functions. So you don't need to actually encapsulate a function inside a class. You can actually just put it there in a file and then have a hard time trying to find where you put it. But we do have packages, at least. So there you go. Very easy, right? Now, one thing that you'll always encounter when we're talking about functional languages is this concept of pure functions. So what is a pure function? Pure function is basically, given same input, the function always provides the same output. And it doesn't really have any side effects. So all it basically is just kind of like a lookup table. And pure functions have this property that is called referential transparency, which effectively means is that if I take that function away and I put in a table with a lookup and says, you know, parameter A and B with values 10 and 5, it gives me this, that's always going to be the result of the execution of that function. It's never going to have any other effect. It's never going to modify any state outside of what you're doing. You just give it some input and it gives it some output. And the whole point of functional programming and is one of the aspects is to try and reduce these moving parts, right? So it's, you know, do as little as possible to alter state. That's why we also try and strive for immutable data. Why do we do that? Because it's less to reason about. If I call a function and something changes over here, now I need to worry about that thing that's changing over here, and which also means I have to test that thing that changes over here based on the input parameters I'm passing in. If I call a function that all it does is just take input and give output and doesn't modify anything here or there, that's less test, less mental image that I have to have. It's just concentrating on that small little aspect. So we try and reduce aiming parts and we try and aim for pure functions. In fact, Haskell aimed for such pure functions that it doesn't have any side effects, which means effectively you can't write a hello world in Haskell. But then they introduced this concept called monads, which allow you to kind of control the side effects of a function. And that's the only thing I'm ever going to say about monads. Okay, so can we achieve our goals? So let's try and take some typical code that we have and see what exactly it means in terms of functional programming and refactoring to functional. So here is a block of code, and can somebody tell me what it does? Something. You can see it right up there. It does something. Right? Right. Brilliant. Someone agrees with me at least. So it does something. You need to look at that code and it does something. If I show you this code, it does something also. Right? Now, which one is easier to reason about? That one or that one? This is crucial, because if you say the first one, we can just end this talk right now. So it's really, really important, and I'm not going to influence you or make you biased, but this one, right? Now, having said that, this one or this one, right? Yes, absolutely, we all agree. Effectively, though, it is, because there's less lines of code, there's less loops, there's less moving parts. And if I look at this, I can say, okay, there's this thing called group by, which, yeah, if I figure out what group by is, which intuitively we know it groups by something, and map, which we'll figure out what it is, but basically it maps something, or it's Google Maps or something, we don't know yet, and a pair, which we know something is a pair, well, then I can basically more or less reason about that, and it's less lines of code. So the question is, big deal, what's functional about that? Well, let's go back and do it slowly. The code that I have here is a list of albums, and anybody that appreciates beautiful music knows I'm talking about Pink Floyd, before Roger Waters left, because then it wasn't Pink Floyd anymore. So this is all of the great albums of Pink Floyd. And what I'm looking for is the top US and UK album, right? So what I do is I take the list of albums and I say, okay, I have a list of albums and I'm going to loop through these list of albums and I'm going to come up with those where the hits were chart UK equals 1 and chart US equals 1, and then I'm going to add them to a list of albums and I'm going to return them as hits. Loop, moving parts, etc. Let's try and simplify that. First of all, let's remove state. So basically, if you look what I've done, the only thing I've done from the previous version is I've removed this variable. And I've used this other kind of like syntactic sugar, which is just a for each, which under the covers actually loops through elements. But what I've done is remove that variable, so I no longer have to think about the state. Okay, big deal. Not a big deal. I haven't done much. Just remove some state. We want to remove state. We want to reason about less. Let's take it a little bit further. I'm going to add some syntactic sugar, some more. Instead of saying for each, instead of doing a for, I'm going to do for each. What is for each? So now already we've introduced something. We've introduced a higher order function. For each is actually a function that takes a function, right? So instead of having a for and inside that having some code, now I've got a function that takes that code inside. This is the convention I was talking to you about in Kotlin where I can drop the brackets, right? So it still actually looks like a for each loop, a for loop, but this is just a parameter, a lambda expression that I'm passing in. Okay? So I've just introduced one little thing which is called a function, but that's a higher order function. But there's still a little bit of emphasis on the how, not the what. If you look at this, I'm still saying, you know, I want something where the chart UK equals 1 and the chart US equals 1. So let's try and improve that, because we want to write less code and we want to write more expressive code. So here what I can do is I can now say, you know what, if I'm looping and I'm doing a condition, why don't I create a function that does that for me? I'll call that filter. Right? It's a very nice name because it filters things out. So I'm going to filter by a condition. So chart equals 1 and US equals 1. That's it. So what's functional about that? Well, if we consider functional that we've now replaced a whole bunch of imperative code with just a function call that takes another function, therefore it's a higher order function, that is functional. That's it. No magic, nothing. All I've done is taken that block of code and passed it as a function, which is the actual predicate. Now, this is very simple because obviously not always is it this easy to just loop through data. Sometimes we need to get data in a different way. So here, for instance, what I have is I want to get the top US and UK hits and the years of the album. So first, I do what I did before, which is filter. But then I go back to that, again, imperative approach, which is, okay, now I want to, for each of these, instead of adding the album, I just want to add the year, right? Why don't I remove that? Why don't I take this another thing of, like, take this concept of a building block of being a function and say, let me try and create a function of that. And guess what that function is? It's called map. It takes a collection of items, it takes some operation, and then it applies that operation to that collection of functions, and it returns another function. It's that simple. That's it. But again, you know, this is very, very simple example. I can get even more involved. So here, for instance, I have a list of albums, and then each album in itself has a list of tracks, right? The manual way, of course, would be, manual in quotes, is, again, take the list of elements, do a for each, and then on that for each do a filter, and then map it. So I've got some functions in there, but I'm still kind of going through this for each block and still trying to tell people what I'm doing. Now, how many of you know what map means? I hope everyone, because I just showed it. Right. How many of you know what flat map means? Right. So map, more people know what flat map means than map, which is really interesting. But okay. Map we just saw. Map takes a collection of items, applies a function to it, and returns a collection of items. Flat maps takes a collection of collections, applies a function to it, and returns a collection of items. And this is what we're doing. We're taking a tree structure. We're taking a collection of items that in itself has items. So instead of taking this code, I can apply this other function, which is called flatMap. And what that does is just flatten it out. Right? So again, we're moving from explicit for eaches and mixing code up and down to just saying what we want to do. And in fact, I don't have the slide, but there's a very, very good slide that I should bring it up with credit. But it's, if you look at the top code here, you can see that there is, if we talk about separation of concerns, which you're all familiar with, there's like, if you try and do separation of concerns here, you can't. You get things that have to do with each other intermixed, right? Whereas here, there is complete separation of concerns. So we're actually trying to create code that is more like separated in terms of exactly what it's doing. Now, having put these two together, which one is easier to understand if I didn't have the function name? The second one, right? And that's important because we need to write code that is expressive, because we sure know as developers, the worst thing we're good at is what? Naming things. Right? So we write functions that are really named badly, and the only thing that we can go by to contrast what exactly the person was trying to do versus what they actually wrote is the code. And we should have both. We should have expressive code and name to make sure that they align, they map up. Because if not, you only have one, and you're like, well, is it meant to do this, or is it meant to do what the code is meant to say it's meant to do? Okay? So we can apply these techniques, these very simple techniques, to common scenarios. And these techniques, if you think about it, is just one simple thing. Primitive block is a function. My function is now my primitive building block. Customer search. How many of you have got a customer filter class? Quite a few. No, actually no one. If I rename that to customer repository and ask the same question, how many of you have it? More. That's not actually a repository. The repository pattern doesn't have any filters on it, but we call it that anyway. Or Hibernate does. So here I have a customer filter by name, which takes a list of customers and a value, filter by country. It's doing the exact same thing, exactly the same thing. The only thing that changes is a conditional. Why don't I remove that and just add a simple function that just takes the customers and just takes the conditional? All I've done there is pass in, create a higher order function. A function that takes as a function a parameter. So now that expression, I just pass in. Same way we did with filter. And I just add it to that. Of course, this could be even better, because I don't need that for, but that's left as an exercise. Template patterns. You know this. You know what the template pattern is? Right? Where you have to define something that is different for subclasses. So for example, in this case, I have a record that has a method called edit record, one that's called persist data, one that's called check permission, and then I have this edit operation which checks permission, edits the record, persists the data. But then if it's a customer record or if it's an invoice record, it behaves differently. I have to do different things. This is called the template pattern. What exactly is changing there? Out of all of this boilerplate code that we're writing, what is the one thing that is changing there? This. So why are we creating all of this boilerplate code for only changing one thing, which is just the behavior? We can pass in, create a function that takes that behavior. Right? Because if we now consider that we have functions as primitive building blocks, we can just do that. Here's an interesting one. Guaranteeing that things take place. So I have an object that is a closable object. I try something, make sure that something, do something with object, and then finally object close. Right? What happens if I forget to close the object? Leaked resource. How is that addressed in Java? Somebody tell me, please. Try finally resource. Yeah. Okay. In C#, that is addressed with what we call a using statement, right? So you do using, and then you take a closable, or in C# it would be a disposable, and then you do what you want, and it automatically takes care of disposing. So I don't have to explicitly call close. Try with resources in Java, right? So you can actually do that. You create a function. So in Kotlin, I can create a function called using, which takes a closable and takes a function. And then it just applies a function and then calls this close on the actual closable object, right? So now I can introduce more correct code and make sure that, for instance, when people do use a disposable object, they make sure that it's automatically disposed of. Because at some point, someone came and said, we now have managed code. You no longer have to dispose of things. And then they said, well, accept these things. So I can now do, val closable object using object and then do something. And then that will automatically make sure that it gets disposed of. Okay. By the way, this again, like this being Kotlin, you could actually use this from Java as well. Or when they take place. Someone asked a couple of years ago, like, does Kotlin have the defer statement that Go has, which is kind of like defer this code and execute it later? Well, no, but you could just, if you start to think of functions as building blocks, you can do that as well. So here is, with defers, print line, defer this, and then print line. So this is going to happen at the end. I just create a generic function that takes a deferrer and then calls the defer right at the end, right? Very typical one is the strategy pattern. So here I have a sort algorithm. And I have quick sort, bubble sort, and then sorter. All of that boilerplate code to create all of those objects and all of those classes for what? What exactly is really changing there? One thing, behavior, right? If we think about it, for many years we have said, we have created classes, we've created objects that contain either data or either behavior. And very rarely have we matched the real definition of a class, which is something that has behavior and data, right? So if, in effect, many of the classes that we are creating and many of the functions that we're creating inside those classes only have behavior, why are we creating those classes? If they only have behavior in response to, but what if I have data? If it only has behavior. So the strategy pattern a lot of times ends up with everything's exactly the same. I create these vast amounts of classes and the only thing that changes is the behavior. Here's a strategy pattern with less code. Right? And of course, now I'm passing in a lambda expression, which is an anonymous expression, anonymous function. I don't have to do that. I can actually declare a function that says bubble sort and pass in bubble sort. I don't need all of the ceremony around it, all of the scaffolding around it, if all I'm doing is changing the behavior. Now, when you start to apply some of these things, of course, coming from an object-oriented background and you start to, you're familiar with a lot of patterns, you're familiar with a lot of ways that you do things, one of the things that first hits you is like, what about my dependencies? How do I inject those damn dependencies, right? So what about dependencies? How many of you have done this? Okay. This, well, not, when I say this, I don't exactly mean this code in Kotlin with these parameters and names, okay? I mean this pattern, because surely you've all created customer repositories and passed in a data access layer, right? But anyway, so here I have a customer repository that I'm passing in a data access layer, and what I do is, obviously, I'm not going to create an instance of data access because that would be tight coupling. What I do is, think about my dependencies, and I pass them in using dependency injection, and then use awesome frameworks that allow me to do really nice dependency injection, whereby I don't even have to worry about anything. I can now just create classes with 3, 4, 5, 15, 25 dependencies, and just the IOC framework will take care of it. Until someone blogs on Medium, and it hits the #1 on Hacker News that says IOC frameworks are evil, right? No, again, IOC is a tool. If you want to kill yourself, it's up to you, right? Let's not blame the tools and the frameworks. Okay, that's not entirely fair because there are some frameworks that we could actually blame. Web forms in Microsoft .NET did a lot of damage to a lot of people. But, in general, it's... anyway, so... This is a typical example where you see with code bases where people now say, oh, this is awesome. I can just pass in my dependencies and not have to worry about it. And then we end up with this. And then when you say to them, this is wrong. Oh, you're saying that I should pass in a collection. No, you shouldn't pass in more than 1 or 2 dependencies. Because if you're passing in more than 1 or 2 dependencies, you don't have loosely coupled code. You have code that is not tied to a specific implementation of some interface. But that class that is passing in 5 dependencies still has a lot to do. And all of those dependencies are there to do coordination. So it's really breaking the single responsibility principle. And we don't want to do that, not because Uncle Bob will get mad at us, but because it makes us more volatile in terms of things that we need to change and reason about. So, but there's another issue that a lot of times, especially for example if you're doing Spring or ASP.NET MVC and stuff like that, you end up with situations like this, which you have like 3 methods and 3 dependencies, and this method is being used by this method uses that dependency, that uses that uses that. And you start to find like, I've got a class, one method is using a single dependency. You've run into that, right? Especially if you're bound to framework code that dictates that you have to do something in that sense. So a lot of times we don't even need all of these dependencies. All we need is a specific behavior by a specific function for a specific method inside that specific function. And we'll see how we can do that. Well, we pass in behavior. That's all we do. We can just pass in the behavior for that function. Why not? Really, why not? If you think about it, dependency injection, all it is just a parameter to the constructor. That's it. Now let's think functionally a little bit. I mean, we're thinking about functions as primitives. I keep repeating this word that functions are the primitive building block, and all we're doing is just combining functions, right? If you look at the functions we've seen like filter, map, group by, all they are is takes a predicate, takes a mapping function, takes a key lookup function, and we just sometimes return functions. And then we're applying this thing, which now is resurrecting, but really it's been around from the Unix days, if not before, which is called pipelining. All we do is just take a function, put some data in it, return some value, pass it into another function, do the same thing. Now, of course, if we all go out tomorrow and start doing functional programming, you know what's going to happen. We're going to have functions with 17 pipelines, elements in a pipeline. And then we go from, let's do this, to write less code and more readable code, to what the hell is going on here, right? Now, the solution to that is not to create intermediate variables. What is the solution to not have 5 or 6 function calls chained? I'll give you a clue. It starts with F, ends with N, and then what you can do is do something that starts with R and ends with G. You can refactor it out to a function, right? So when you have 5 functions, hey, why don't you refactor that out to a function that takes parameters or functions? So you still can keep code readable and not do things like this or have long pipelines. So how do we reuse? We need to be able to define these functions to be able to reuse. So some languages offer you really good aspects, like for example, Haskell offers you function composition. Here I have, for instance, a function, because you know, if functions are our building blocks, we want to be able to reuse them. So here I have a function sum, here I have a function squared, and here I have a composition of sum and squared. As long as the parameter of the input matches the output of the next function, I can combine them. Right? And now I can create a new function that combines both. Kotlin natively doesn't have composition, but you can create a function that composes 2 functions. Right? In functional programming, there's this very common concept called currying, which comes from Lambda calculus and Haskell curry, the guy behind Haskell. That's why also in terms of the reference to currying. What currying basically is that if we assume that a function can only take a single parameter, what currying does is take functions that take multiple parameters and it returns functions that only take single parameters. So what does that mean? Here I have a function sum that takes 2 parameters. If I curry that sum, now Kotlin again doesn't have currying, but I've created a function to curry a function. What that does is give me a sum curried. So now if I do sum curried 3, this looks weird. Why? Because sum curried 3 is not going to calculate the sum of 3. It's going to return a function where the first parameter is 3 and only takes another parameter. So now I'm doing sum curried of 3 with 2. That's what currying means. And you say, why the hell did you just throw that at me? I'll tell you in a second. Here's an example of sum curried with 3 parameters. So now I can do sum curried 3, we return a function where the first parameter is 3, and now I do a 2, we'll return a function where the first parameter is 3, the second parameter is 2, and then I will call that. That's why I could call this, for example, sum curried 3 and 2. So basically what I'm doing is redefining function with default parameters, which is different than a function with default parameters. Because the first executes a result, the second returns a function on which you can then invoke. Why? Well, a lot of times, and talking about dependencies, when you want to pass in default behaviors, you don't want to have to redefine that default behavior over and over again. So you can do things like partial function applications, which requires currying. And here what I have, for example, that checkout controller that I showed you before, by default, I can say, you know, this is going to use the cart repository. So here I can create a new partial function, which basically this is giving me a new function where the checkout handler has a new parameter passed in, which is cart data. Okay? And this allows you to now use this allows you to define functions where certain parameters are passed in by default. And again, this is very different to I now have a function with default parameters. And now I can reuse these functions. I can compose functions, I can define partial functions with default parameters and use them here and there. So here's, for example, the application of sum number with 10. So where I'm doing sum partial 10, I'm creating a new function where I only pass in one parameter and the result is always 10 plus that parameter. Okay? And then there's the data. All we're doing basically is we're just taking data, we're processing it in stages. That's all we're doing. So what is our data? We have customer, invoices, points, age. We have date of birth as scalars. We have list of collections. We have list of invoices. We have sets of pairs. But if we think about it, really all we're doing in our lives is creating functions with data taken as input and applied as output. We take lists and we output lists. We can combine these. We can do map, flat map, find all, merge, zip. We can obtain scalars from these lists. We can say, take a collection of items and give me the first one. Give me the last one. Find something that matches some predicate. Aggregate them, right? And many functions, many of these things that you see when you start to do functional programming, all boil down to a couple of functions, one of them being fold. How many know what fold does? Right. Fold, graphically, is this. I have an array of elements. I have a function where I have an initial element, which is accumulator, and then I have a list of elements. What is fold? It takes the first element with the accumulator and it produces a result. It then takes that result, applies it to the second element, to the third, fourth, fifth, sixth, until it produces a result. That's it. That is what a fold is. It just folds the list. And there's fold left, there's fold right, which folds from this side or folds from this side. And this is very much linked to concepts such as recursion, because when we're talking about recursion, about functions, a lot of times we try and reduce elements to a list of collections to smaller collections and then work on those collections, and that's what recursion is all about. Here's an example of a recursive maximum. It's very simple. I have a list of items. If it's 0, I cannot operate on it. If it's 1, I return the first one. If not, I return max. Now that is expensive, like all recursions can be expensive. We want to avoid recursion. What is that? That is the initial value. It's the first value. Okay? I can take that same recursive function and implement it using what? Fold. Right? Where the first element is 0. That's all I'm doing. So a lot of recursion can be actually translated into folds, which is way more efficient, right? And in fact, there's another one which is called reduce. There's another function which is called reduce, which is basically fold with a default accumulator. That's it. Okay. We spoke about immutability, and that's its own topic, but the idea around immutability is you try and avoid state so that you reason about less things. You don't have to worry about all of the moving parts. That's the thing. I now just have these primitive building blocks where I can put in data, get data out. Put in data, get data out. Don't worry about all the state modifications, etc. And when we start to do that, we start to not have to worry about everything that could potentially go wrong around us. Now, not every language allows for mutability by default. Kotlin has val and var, Scala has val and var. Java, you can kind of simulate it with read-only, but you've got to also notice that none of these propagate. So if I, for example, create a class with 3 read-only properties or 3 val properties, that doesn't mean that the class cannot be immutable unless it's closed or final or not open in Kotlin, and so you can't, there is potential where you could override, inherit from that class and make properties mutable. So it's not just adding a flag always. But we try and consciously avoid state. And one question, of course, that comes up, this now gets into a little bit deeper territory, but one question that always comes up is, but if I have all these functions are calling each other, and if I've got this enormous stack trace, surely this is going to have a performance impact. Surely. Yes. Of course it is. And that's the reason your application is slow. It's got nothing to do with the internet. It's got nothing to do with the database. It's because of the call stack. Right? No, but there are some times where you do wonder about performance. And how does this impact? So this is Fibonacci. Have you all known Fibonacci? Yes? One of the most annoying things that they teach you when they're talking about functional programming. Yes, that is very slow. 20 or something like that. You start to hit it. You can go grab a coffee, have a shower, come back, and it's still calculating, right? But you know exactly what it does. I look at it, it says return 1 or 0, or else return the result of Fibonacci minus 1 and Fibonacci minus 2. Here's the iterative approach. Very fast. What does it do? Oh my God, I don't know. Right, I've got to look at it. So what do you do with these cases? There's this technique that you can use, which is called memoization. Memoization, this is the Fibonacci memoization specific case for Fibonacci, which basically means if I'm talking about functions being just a lookup table, and where I have a function that keeps calling itself with different values, and some of those values are already being calculated, which is one of the reasons why Fibonacci is slow, why don't I just memorize that? I can cache that result. If you this is very naive implementation of memoization, but if you run this, it will run at the same speed, to the site of I, as the iterative approach of Fibonacci. And it won't hang. And it's still recursive, right? But it's memorizing values. So it looks it up, it says, oh, it's already there, I don't need it. This is also interesting because some compilers have this concept of tail call. Is this a tail call? You know what tail call is? Where the last call is to the function itself. Is that a tail call? No, because the last call, it has to keep the stack because it has to multiply the result, right? Now you can convert non-tail call recursive functions into recursive functions that are tail call functions, tail call recursive. So this is taking the factorial and making a tail call recursive, and then some languages, for instance, Kotlin, allow you to add an annotation which is called tail recursive, which basically means that now it will convert, when it does bytecoding, it will just replace that with a goto. So it's as efficient as just a for loop. Okay. Other techniques, of course, that you can do, Kotlin and other languages do this inlining. Inlining is when the parameters don't, there's certain scenarios where, instead of maintaining a call stack, the compilers can inline the actual call. So it's just kind of like copying the code of that call and pasting it inside the function call. Okay? So these techniques allow for optimization. Now, if you've noticed, I've not mentioned a lot of the things that you sometimes encounter when you're talking about functional programming. I only just skipped over monad. I haven't mentioned anything about functors, but we've already seen functors. A collection of A whereby you can apply a function A to B returning a collection of B. Map is an example with a collection of a functor. Monads, I've not made that terrible word monads, right? But we've actually used monads in different ways. The maybe monad, which is the option in Scala. The list monad, IEnumerable, iterable, the equivalent in Java, is in C#. Promises are kind of like a monad. But I've not concentrated on monad because when I started to look at the functional programming, I was put off by monoid, monads, functors, endo-functors, which is just a functor where the collection is itself. And it's kind of like, do I really need this? And I looked at it from the aspect of, you know, what exactly do I need? What is the benefit that this is providing me? What will I gain out of functional programming? Why would I even be interested in this? And I looked at the aspects that I said at the beginning, which is write less code, write more concise code, write more readable code. And I'm not saying that you don't need these concepts. Far from it. It's very interesting to understand them, and you can get into other things and learn more about them, and you should, I'm still learning, and we should learn more. But these shouldn't be reasons that you shy away from experimenting new things. And if you look at this presentation, the main takeaway is just, you know, let's start to think about functions as our primitive building blocks, right? Let's start to embrace them as primitive elements. Instead of now thinking always about objects, classes, methods, let's start to think about functions. Let's focus on writing less our own code. The for each or the filter, this isn't magic. If you drill down into either the library or the language, if it's native to the language, it's just doing the same thing that we've been doing. Except we don't have to worry about doing it anymore, which means we write less code, which means we have to test less code. We focus on writing more descriptive code, not intermixing different aspects, different concerns, but trying to separate things out. And when we start to pass in behavior with functions, it allows us to do these things. And we write deterministic code by not having to worry about if I call something, what happens to the surroundings? What happens if, you know, this state gets altered there or that variable is set somewhere else, right? And the thing is that this is not rocket science. This is about what value does this provide me in my day-to-day work, and how can I leverage that value? And start with that, and then from there, use it and take it further. Because at the end of the day, I can't convince you that something is good unless I tell you that it provides you with value. Okay? Some recommended books that I do think you could look at, there's one called The Little Schema, which is a copy of The Little Lisper, but in Scheme. There's also A Little Closurist. It's like a story with a little mouse, and it teaches you a lot of the concept of folds and recursions and functional primitive blocks. Learn Your Haskell is a website, which is really great if you want to learn Haskell. And my one mistake was not paying attention to Haskell in university. I should have. And Functional Programming in Java is by Venkat, which is a fantastic book. And it teaches you some of the things with Java 8 and how you can leverage that on your daily work if you're using Java 8 today. Okay? And with that, we're done. Thank you. And I'm going to be at the booth today and tomorrow, the JetBrains booth. So if you want to stop by, more than welcome.